Hello guys, welcome to today's video. Today we are going to do something really cool. It's again at the intersection of complex analysis and function analysis. So we are going to see what holomorphic functions are, how the resolvent operator that we defined above in the previous video relates to the holomorphic function, and the dance of all these equations around concepts. So let's start with seeing what a holomorphic function is. So I have let X be a non-trivial complex Banach space. I'm here, and U be a domain in C. So by domain I mean a non-empty, connected, and open set. And a function from U to X is analytic in U if for every lambda naught belonging to U it has a power series representation. I'll come back to this in a minute, with center lambda naught and positive radius of convergence. So three things to unpack here, as I can see. So I initially saw that there is a function defined on U. This function is f. I am calling this function to be analytic if it has a power series representation. So this equation that you see, and well, this is what I mean by a power series representation. So I say that a function f is holomorphic in U if and only if at every lambda naught belonging to U it has a power series representation, which is given like this, and with a non-zero radius of convergence. So by non-zero radius of convergence I mean that this power series converges when for some r. So it converges in this region. So if you have lambda naught and you define a lambda within this region, then this power series it converges. So it has like a finite value. This is what I mean by convergence, and is equal to f lambda in the radius of the disk. So this is the concept. And in other words, if you give me a lambda naught, I will find your power series or the ANs. By finding power series, it means finding these coefficients, finding these complex coefficients. In our case, when the domain is C and it is going to X, which is just a Banach space. So by finding a power series, it means that finding those ANs such that this converges in this region. So the power series converges in this region and is equal to f lambda in that region. So this is a basic idea into what's about to happen in the time to come. And so start like for every lambda naught belonging to U. So I can also say that for every lambda naught belonging to U, the function f has a power series representation with a positive radius of convergence. It just means that this r that you saw above, it's greater than 0, this r, so that f lambda is equals to this quantity in this region. And so I can, in order to get the final gist of this, I can also say that for every lambda naught belonging to U, I can find an r, and I can find ANs such that this power series converges given lambda minus lambda naught is less than r, and it converges to f lambda. So this is the idea behind what an analytic function is. And now I'm going to define my resolvent as an analytic function. So if we come back to the theorem, we'll come back to the theorem in a minute. So the idea in the theorem, before even showing you the theorem, I'll give you what's going to happen and what are you going to see in there. So the idea in the theorem is basically that the resolvent is an open set. So what I mean to say is that for every lambda naught belonging to my resolvent set rho t, I can construct a ball, construct an open ball with radius 1 over norm of r lambda naught t, and this ball will lie completely within rho t, and that's just it. So the only takeaway in the first part is that resolvent is an open set, because for every lambda naught belonging to the resolvent, I can construct a ball with radius 1 over norm of r lambda naught t such that the ball is completely within the resolvent. And second, I'm saying that this power series, so I write r lambda t is equals to the summation from 0 to infinity minus 1 to the power n r lambda naught of t to the power n plus 1. So this is just simply r lambda t to the power n plus 1, lambda minus lambda naught to the power n. And I say that this power series converges inside the ball. So within this ball, the power series converges, and it converges to r lambda of t. So that's the basic takeaway from the theorem. The second part just says that the power series given by this r lambda t, it converges in this ball, in this ball around lambda naught. So if I've given a ball, if given a point lambda naught in U, I construct a ball with this radius, and within this region, this power series r lambda t, it converges, and it converges to r lambda t. So guys, till now what we have seen is that rho t is open, so that sigma t is closed, and the resolvent function r lambda t is analytic in every domain U, which is a subset of rho t. So now let's move on to other things. So I have this proposition of resolvent identities, and it's just linear algebra, and I just need to make sure that my linear operator t is closed. So it is these two identity holds for closed operators, so they should also be holding for continuous operators. It's just a trivial identity, they are very trivial proofs, but after that we go to some really full power topics. And now before I get into them, I would like to tell you a few things about all these functions, how they are behaving. So, well, a function f, start like this, it takes x to the value of the function at x. So if I have an x and if I apply f to it, what's really happening is that this function is taking x to its value at x. So f, this is the flow, and similarly, so the derivative is taking x to the value of the derivative. So essentially f dash is taking x to the value of x at f dash. That's the derivative function. So f dash is a derivative function, and it is taking x to the value of derivative at x. Now you can only be holomorphic in the domain, and all that means is that you are complex differentiable in the domain. So just saying that if you are complex differentiable, and I say that, okay, I have given the definition of complex differentiable. So I have x as my non-trivial complex Banach space, and U, let's be its domain in C, an FB function from U to x. And I define the complex differentiable function f as follows, and I say that suppose that f is complex differentiable at every point in U. We say that f is holomorphic in U. So if it is complex differentiable at every point in U, then it is holomorphic in U. And complex differentiation just means this thing. And the function f dash from U to x defined by lambda, it takes from lambda to f dash lambda is the derivative of f. So that's basically what I mean by holomorphic functions. And similarly, I have just given a toy example here explaining the concept that what it means the defining derivative at a point and the derivative function. So derivative at a point is just a real number or a complex number depending upon the space you're in, but a derivative function takes element x to the value of its derivative. So that's a couple of things. So what we have seen till now is the definition of complex differentiable. What it means, it just means this definition, that the limit exists, and I say that if a function f is complex differentiable at every point in U, we say that f is holomorphic in U. And then we come to some other facts. I say that, okay, let X be a non-trivial Banach space, U be a domain in C, and f be a function from U to X. Now I'm saying that if f is analytic in U, then it is holomorphic in U. So it is just a statement, you just need to know the statement, and it follows from a huge proof in complex analysis. It goes on for several pages. For the purpose of this class, I just want you to keep this statement in your mind, that if f is analytic, then it's holomorphic. And what comes next is, okay, well, the gist of this statement, this proposition, is that analytic functions are holomorphic. And now I see that, okay, I'm saying that let X be a non-trivial complex Banach space and T be a closed linear transformation. Now the resolvent function lambda to R lambda T is holomorphic in every domain of U, which is in rho T, and moreover this identity holds, so this equation holds. Now let's break it down into two parts. Well, if I write the equation of R lambda, and if you go back a bit back in the video, I had defined R lambda to T to be like this. So if you look at the definition of R lambda T from up, you will see that this is how the equation is written, and when you differentiate it, you just get this. Now one very important question that you might ask me is, how can I just differentiate it and get the result? So what I want to say is that R lambda T was defined as lambda I minus T inverse. It's defined like this, and I'm saying that if you differentiate it with respect to lambda, then you would get this quantity. Now if you just write R lambda, square it and multiply it with -1, you'll get the same result. And when you work out the maths, you'll see that it's just as if I did d by dx of this operation, and I just took the derivative inside the summation and I got the result. Now, so I can take the derivative inside the sum only within the radius of convergence. So I can do these kind of stuff only within the radius of convergence. This is the importance of this corollary, that differentiation is allowed term by term in a power series within the radius of convergence. So if I am in that area lambda minus, so let me write it finally, that if I am in this radius of convergence, meaning in this area or in this disk, then I can do the same. And if I do d by d lambda of lambda I minus t to the power -1, then the result is, well, minus of lambda I minus t to the power -2. Now in the first glance this might seem completely strange, out of order, and the reason is, well, it should look very weird to you because this t is not a number, this t is a function in an LXX, and I cannot just use the results that I learned in calculus to do calculations in the scenarios here, because this is not either a complex number nor a real number, it is a full-blown function in LXX. But the power that I'm getting here, or the beauty of this corollary, is that I can forget the fact that we are in LXX. I can just follow the rules of calculus that I learned and apply that differentiation here, given that I am operating in this region, given that I am within the radius of convergence. So if that is the case, then the derivative of lambda I minus t inverse can be written as minus of lambda I minus t to the power -2, and this is exactly what the statement says. And finally, we are gonna discuss this theorem. And this theorem says that let X be a non-trivial complex Banach space, U be a domain in the complex plane, and S be a mapping from U to LXX. Now S is holomorphic in U if and only if the complex valued function Z from T as Zx is holomorphic in U for every X belong to X and every T belong to X star. Now I know that in the first go it feels way too much to take on to, but if we take a deep breath and just focus on this diagram, then I think I can help you understand this concept. So what was happening before? What was happening before is that I had a domain U in the complex plane, and I had a function f, and I said that for holomorphic functions there's a huge category of results that is called complex analysis. So what I had initially is that a function f which takes an element from U to C. So this function f is given from U to C, and I say that okay, this function is holomorphic. Now I want to say that a function S which takes lambda or U to LXX. So this, let me write S, it takes U to LXX. Now I want to say that this is holomorphic, this S is holomorphic. And the reason I want to do it, because if I can prove that this S is indeed holomorphic, then I can use those huge catalog of results that I had for complex analysis and apply it here. See? So what shall we do? So this theorem essentially tells me that S is holomorphic in U if and only if f tilde from U to C given by f tilde of lambda is equals to L S lambda x is holomorphic for every x belong to x and for every L belong to x star. So for all values of x in my Banach space capital X, and for all values of L in my space x star, if this mapping L S lambda x is holomorphic, then I can say that okay, S is holomorphic, and the other way around also. So again, I had a function f from U to C which was holomorphic. Now I want, and I have a huge range of results for holomorphic functions. Now what I'm saying in this theorem is saying that a function S from U to LXX is holomorphic in U if and only if the function f tilde given by f tilde of lambda, which is defined as L S lambda x, is holomorphic for every value of x belonging to capital X and for every value of L belonging to the dual space of X. So if this function is holomorphic, then I can say that S is holomorphic.